Okay, everybody, this is our last official talk of the day before our closing remarks. What you're about to see here is a structured threat for shareable, actionable, and implementable threat intelligence, which actually sounds like a really interesting topic. Our speaker today is Rita Foster, and if you have any questions for her during her talk, you please put those in track one chat. I'll be monitoring that for the Q&A period at the end. So, Rita, whenever you're ready.
Thanks, Brian, and thanks again, B-Sides, for getting everything together to host this event virtually. I really appreciate it. So I'm Rita Foster. I'm from Infrastructure Security. I'm a strategic advisor, which means I get to align all the research that we're doing under infrastructure security. Been at the lab for 30 years, mainly working on control systems. Last for 15 years working on the cybersecurity of control systems. And probably about 7 years ago, it was really getting mundane. I was like, when are we going to ever win? When are we going to ever have something that we can do that'll really be a change? And what happened is that a group of people in California came to us with an idea, and we were able to help be part of a very much larger team. I think you heard Scott Kramer talk about collaboration. That is the key to great use. And we were able to create some actionable, shareable, implementable threat intelligence. So with that, I want to introduce you to the California Energy System for the 21st century. It was funded by the California Public Utility Commission. California has a very aggressive renewable energy portfolio standard. They know that if they're going to put all these devices on their electric grid, they have to ensure cybersecurity from the get-go. So they were able to have Lawrence Livermore as the lead national lab for this activity. We were joined with Lawrence Livermore and a company called New Context out of San Francisco, a startup company. And our role at Idaho was to take the asset owners, the Southern California Edison, the Pacific Gas and Electric, and the San Diego Gas and Electric test beds. They provided large test beds and substation automation for distribution, transmission, and energy management system. We were able to instrument those to figure out if we could do response and detection capabilities without impacting some of these very sensitive equipment that has a really quick response time, make sure we don't have any latency issues. And also just generally help with the testing of automated response and develop tools around that. New Context came to us and said, you know what, we need to use a standard language. We can't all speak differently. And that was so true because every single test bed was different. The substation automation for distribution was worlds apart from the substation automation for transmission. The energy management system was way different. There was nothing that was similar, nothing common. And in their security products, the same could be said. One utility was a Splunk shop, another one Forescout, another one IBM QRadar. So it was all over the map, and we knew we needed something that could work with all of that. So structured threat information expression is an international standard. It's been around for decades. It's open source standard. And they kept evolving and they kept changing. And from that, we were able to develop a lot of tools that I'm going to demonstrate for you today on some of these products. Everything you're going to see is available on INL's GitHub sites. There's 2 applications and 2 utilities. The first application, we have a really fancy video. It's called Structured Threat Intelligence Graph, created by Jed Hale with help from others on our team as well. So I'll let this video play. It does have some sound on it. Let's hope that works well. If not, we have some other videos without sound. So we'll try this.
In 2015, the first known cyber attack against an electrical grid turned off electricity for 225,000 customers in Ukraine. Since then, cyber defenders have identified and neutralized thousands of cyber attacks on critical infrastructure in the United States. If successful, these attacks could have crippled the power plants, substations, transmission lines, and transformers that provide electricity for millions of Americans. One of the primary tools for stopping those threats, the Structured Threat Information Expression Software, or STIX, has become the global standard for identifying and sharing cyber threat information. However, the STIX software produces thousands of lines of complex computer code that can take experts a long time to untangle. To make STIX more user-friendly, researchers at Idaho National Laboratory developed the Structured Threat Intelligence Graph, or STIG, software. STIG translates dense threat analysis code into easy-to-understand visual icons. With STIG, power grid operators no longer need to comb through thousands of lines of code to pinpoint a vulnerability. The software automatically highlights adversarial behavior and maps connections between threats within hours instead of weeks or months. As the threat evolves, grid operators can quickly determine which assets are most in need of a correction or an update. Further, STIG's simple visual format allows cybersecurity personnel to easily share threat information, drastically reducing response time. It also makes it possible for people with less technical expertise to easily understand and respond to an imminent threat. The software eliminates costly delays to updates that are meant to stop a virus, malware, or deliberate attack. STIG can be used alone or with tools that automatically respond to a cyber attack proactively by identifying a cyber adversary's attack behavior and rendering it useless. INL researchers have released the source code online free of charge in hopes of challenging other developers to protect the nation's critical infrastructure systems. In short, STIG's picture is worth much more than 1,000 words.
So I hope that sounded okay and you were able to see some of that video. That was a nice, well-produced video on what we did with the Structured Threat Intelligence Graph. I'm going to go now more into details of why we developed it. One reason we developed it is because we're lazy and we didn't want to program too much in XML or JSON. STIX 1 was XML. STIX 2 is JSON. When Jed Hale saw that it was JSON, he said, hey, that's object-oriented. Why don't we put it into a graph database and make it visual? And that was the start of STIG. We created STIG to use for automated response capabilities. So here you're seeing that we've gathered some threat information from the internet. I think this is like Draco's report on Indestroyer or ESET's report on Indestroyer, crash override. We pull in the attack patterns from MITRE. We pull in some assets that may impact from that. We query in, we query out so that we can gather some other information. Earlier, we created an indicator of compromise, which looks like that thumbprint, where we're detecting the squid proxy, which they use for the command and control. The adversary was Electrum, but now we're going to create a different indicator, and that indicator is going to detect whether that relay becomes open. In the electric grid, if a relay becomes open, that means the power goes out. And that's what happened in Kiev 2016, is that they opened up breakers and they had a major outage. This is the indicator. It's looking for a couple of different IP addresses, source and destination and ports, and a little teeny piece of binary command that says, I'm going to open up that breaker. We know what that is because we have the test beds. It is in our lab. So we know what that binary looks like, and we can detect that. We're adding that to the indicator. So the indicator is not a static indicator. It's not a hash. It's not just blocking an IP. It's looking for a pattern. It is a regular expression. By adding the MITRE attack patterns, or KPEC here, you're also getting some more context into what the problem is and what is the behavior of that attack and how can you solve it. We created 17 lines of unique code. There's a lot of Python code in that one middle line there, which is going to look for a couple other things on our substation automation and detect whether we can reclose that breaker safely. And we're putting that into a course of action. That is that green box with the medical cross box on it. The course of action is full up turning programming code. We can do whatever we want. It's not just a regular expression. This isn't a visual database, or it's in a graph database, which allows you to do a lot of different visual area things. But then it produces validated STIX code. And that's the key, because STIX is the standard that's international. It's been around forever. When we did a survey, there was over 300 different security products who use STIX. So with 18 lines of unique code that we created, and then pulling in things from the internet that had other references and context, we create a STIX bundle of over 300 lines of JSON code, which now can be translated into automated response technologies. We use this concept with new context threat monitoring appliance, which you're seeing on the right here, where they select how they're going to indicate something is happening by looking at the packet captures or looking at the data as it's going across the internet. And then bam, it turns green, which is bad in the electric grid. Red is good because it means the power's flowing. And that's how fast it works. That's how fast that code works to detect and to respond. It takes longer to get the cyber observables together so you have a complete record. And that's what's happening now, is we're looking at the cyber observables that prove, yes, I saw those states, and yes, I reclosed. That's what we used it for, machine-to-machine automated threat response. What you're seeing now is the oil rig campaign. The oil rig campaign was a malware that went against Palo Alto networking switches in the Middle East. It impacted tens of thousands of network switches. It was a very nasty exploit. But Palo Alto and Unit 42 did a beautiful analysis of this. They have all these little yellow squares here that are indicators. It has blue attack patterns that are associated with it, so you can associate it with some sort of other behavior. It has the campaigns. There was actually 3 campaigns on there. What we did is that we eliminated 2 of the campaigns and just focused on one, pulled in the malware and the attack patterns from MITRE. And then when you change the view, you can understand what you need to work on. That little blue attack pattern way on the right, that's what you need to focus on. If you can mitigate that attack pattern, you can get rid of all those indicators in an inner circle, all the other malware. Bullrig's a very big campaign, it's that large. But a tool such as Structured Threat allows you to do this. Now you're seeing some of the work from 2019 interns. They were able to use Structured Threat Intelligence Graph and test out their response capabilities on our test beds. I was able to demonstrate this on Capitol Hill. So our interns' code and their results were actually shown on Capitol Hill last year. So that was exciting. But it's a very easy tool to pick up. It's great if you know some programming. If you don't, it is very visual. It's like a visual programming tool. And again, the thing with STIX 2 is that it now is more object-oriented. It's JSON. You can do regular expressions in your indicators of compromise, so they don't have to be static. And in your courses of action, you can do pretty much whatever scripting you want. So it's extremely powerful. So we showed you a little bit how we created indicators and courses of action for crash override or indestroyer, and that was the blackout in Kiev that targeted the transmission system of the power grid. We showed you how you could use it for other more threat analysis work, such as huge threat analysis capabilities from Oil Rig, pulling down threat that other people have provided, and doing your additional analyses. And then the next product that we worked on was, how do you score? There's so many cyber issues out there. How do you know which ones you should be working on? We were able to view a whole bunch of very large security operations centers from these very large utilities. And there's so many different scoring systems that the federal government provides for you. There's common vulnerability scoring. But the thing that's always missing from any of these alerts is your ability to defend. What is your configuration you're trying to protect? And that's key. So this next application is for tracking and prioritization of the new cyber issues that come up. You're figuring out applicability. Applicability isn't a binary, it isn't a yes or no, because we all know that when a malware comes out or an exploit comes out, it can be modified to be applicable to others soon. Sometimes there's a lot of information about what the exploit, malware, and vulnerability is. Usually over time, you get more information. What is your ability to defend as that defender? Do you have the tools that you can do a defense? Can you do automated response? Do you have to stop and rebuild in order to do any sort of response? Then there's the consequence concept. Does it impact your control system or does it just impact your company? Here you're seeing side-to-side comparisons of WannaCry and NotPetya. They both use that SMB channel as a problem. And you can see here that the NotPetya had a lot larger consequence because it was modified for specifically to work on control systems. And then at the end, you can create standard STIX objects here that you can go and put back into STIG and refine for your specific indicators, your specific courses of action. That's the output for exploit, malware, and vulnerability scoring. So STIG and EMV are the two applications that we created under the CES 21. But we knew there would be other things that we would want, especially to share with other partners. So what we did is we created a couple of other capabilities. We created something called Structured Threat Observable Tool Set because it had to be a palindrome according to our team, and I didn't want Taco Cat. Anyway, STOTS is an amazing little utility. STIX works on this concept of indicators of compromise, courses of action, and cyber observables. STOTS creates those cyber observables. We can create an agnostic detection system, sensorless. One of the things with control systems, everybody wants to put a sensor someplace on a network. Nobody has the time to keep those sensors going and running, and some of these networks are pretty fragile. There are a lot of them are very legacy systems, and you just don't have the resources to go through all this stuff. What STOTS allows you to do is provides a framework with many engines that you can look at deep packet inspection inside the packet engine. You can figure out which nodes on the addresses are adding or leaving. You can look at files on different systems, including embedded systems, to figure out if someone changed a configuration, which is extremely important in the electric grid. You can work with your security information event management systems, go back and forth between the IT and OT integration. We proved this out with Elastic, with QRadar, Splunk, Forescout, and I'm missing one, but many different security information event management systems we were able to integrate with this response capability. We have a very preliminary capability of figuring out which processes are running on that system, whether it's an embedded or whether it's a full host computer. A file engine will do file engine changes so you can detect if something rogue is out on your file systems. And a command line engine from command history on Bash. You can actually figure out, did somebody put some command in there that you really don't want them to put? I don't know, RF minus RF, I don't know, RM minus RF. And then the last application, that's not an application, just a tool set, is what we were able to do is leverage another project. The validation and measurement of automated response was funded by the Department of Energy. Those test beds in our lab were very expensive, large test beds. We were able to instrument them, take performance metrics, see what impacts automated response had. And then we wanted to create a tool that allow an automated response action to happen. So as STOTS creates the cyber observables, STAR will work on those cyber observables and execute a course of action. That's what structured threat automated response does. It's very rudimentary, but it's a really good way when we work with our partners that they can get a concept of how to get automated response through these activities. So again, interns have used these tools with great success, and these tools can work together. A new emerging cyber issue comes about, you can score it in EMV to see if it's a concern that you can do something with. You can go and analyze it further in STIG to create your tailored indicators and your tailored courses of action. You can use the utility STOTS to actually find out, do I have applicability? Can I detect something happening on the system? And then you can use STAR to figure out how to mitigate that for a course of action, creating an agile course of action that can happen through operations. And this is very important in an operational environment for control systems. We're taking the structured threat concept further. We are in our first year of doing Geo Threat Observable, also funded by the DOE. We are taking a bunch of STIX data and we are putting it into a nice test corpora, and we're running machine learning to see if we can get to a predictive capability of cyber threat. We're going to have still the focus on indicators of compromise that are not static, and courses and potential courses of action that can be let alone shareable, but implementable, let alone very actionable. Our other two projects that we have that use a lot of machine learning on reverse engineer binary. I think you heard Sage Havens in that panel earlier. She was one of the main people who worked on some of this reverse engineering test corpora. For deep learning malware and for firmware command control, once we identify what the problems are, you know we're going to describe it in STIX, and we're going to use these structured threat tools to describe it so it can be shared. And that's what I have. These tools are available. And are there any questions? I think you're muted, Brian.
You're right, I am. There are not currently any questions in Track 1 chat, but that was really cool stuff.
I'll tell you, we have a lot of senior programmers and people, cybersecurity researchers, and we were all getting down in the dumps because we got so tired of just getting beat up all the time. You never get a win.
Right.
And then being able to create something that's agile, that can work, that isn't this big, huge, heavy lift of we're putting sensors everywhere and you're going to look at 1 terabyte of logs every single day. And you're going to decide what to do. It's like, oh no, this is very, very tailored, very targeted.
Yeah.
Very surgical.
Very proactive.
Well, it's for somebody who owns the system, right? It's
right.
You're not going to do this unless you actually know what your system is.
Right.
That's definitely.
It's very cool.
Yeah, it was a lot of fun to do that. And the other thing that we really like about structured threat is we get so tired. I mean, there's some absolutely beautiful, gorgeous threat reports out there. They have great pictures and graphics, and they have great explanations. But then what are you going to do?
Right.
The better ones will have STIX associated with them. They will have, so, you know, if it's a Yara rule, we can put Yara rules in STIX. We can do other areas as well. But STIX is that framework that allows us to share, and it works with so many security products that if you want to use the automated response capabilities of a Forescout, you can, you know, or a QRadar, you can. You don't have to use what we've developed. You can use that. So that's what we really like about it.
Cool. I think that'll probably do it for today.
Okay.
Thanks very much for your time. We greatly appreciate it.
Right. And looking forward to those final comments. And thanks again, B-Sides, for putting this on.
Thanks,
Rita, I have to say too, I mean, just really fabulous. And it reminded me a little bit of Maltigo. I don't know if you guys.
We've looked at, you know, when we're doing research, we usually do a survey of who's doing something similar. And then halfway through the research, we do that again. And then at the end, we do that again as well. So yes, I understand what you're saying, but this is very surgical. It's not, besides the structured threat intelligence graph and the EMV, it's not very flashy, but it's for response capability and detection, it's agnostic and surgical. So it was pretty fun to do that on the variety of test beds we had.
Cool. Okay. Well, thanks very much.
Great. Thank you, Brian. Thanks, Sandra.
Thank you, Rita. You're awesome. You know, with it just being us, and we talk about women in cybersecurity, you're just such an inspiration to all of us. You know, you're just amazing. So thank you so much for presenting at B-Sides. We really appreciate it.
Thank you.
Bye-bye.
Bye-bye.